Recursive Flow Matching by Jiahe Huang, Sihan Xu, Sharvari Vadgama, and Rose Yu. Imagine trying to predict the trajectory of a catastrophic hurricane, but your AI model takes longer to compute the forecast than the storm takes to hit land.
Right, the classic speed-fidelity trade-off.
Exactly. Generative models for simulating complex physics, like fluid dynamics or climate, they face this massive bottleneck. They require tens to hundreds of inference steps, making real-time use impossible.
It's a huge problem.
Yeah, but this paper introduces recursive flow matching, or RecFM. It's a simulation-free framework that models a family of trajectories across different scales and enforces self-consistency among them.
And the results are pretty wild.
Right. The result is a model capable of high-fidelity 1 to 2 step generation, achieving up to a 20x speedup over state-of-the-art diffusion emulators. Plus, it reduces mean squared error by over 15% compared to vanilla flow matching.
It's a massive leap.
So, welcome to AI Paper Slop. For this breakdown, our mission is to unpack the math, the architecture, and the theory that makes this one-step generative physics emulation actually possible.
Well, to really understand why a one-step solution is such a breakthrough, you have to look at exactly why existing models choke on these physical simulations.
Right, because if you're an ML engineer working on this stuff, predicting system evolution is the whole point.
Exactly. And historically, we relied on traditional numerical solvers, methods that discretize space and time to solve explicit equations.
Very accurate, but incredibly slow.
The computational cost is just astronomical, which is why the field shifted to data-driven approaches like physics-informed neural networks, or PNNs.
And neural operators, right?
Yeah, exactly. But those struggle when your governing equations are incomplete or highly stochastic.
Because if you're modeling, say, global climate, the deterministic equations alone just can't capture the chaotic reality of the system.
Right. So generative models, specifically diffusion models, they bridge that gap between statistical learning and physical laws.
You can just train a diffusion model on observational data and let it infer the dynamics.
Exactly, without needing the explicit formulas. But it introduced that iterative bottleneck. You might need 100 sequential denoising steps just to generate the next state.
Which compounds catastrophically if you're rolling out a long forecast.
Right. So researchers introduced continuous normalizing flows and vanilla flow matching to learn these probability paths without simulation during training.
And vanilla flow matching removes the iterative overhead during training, but during inference, there's this critical trade-off.
Yeah, if you try to reduce the sampling steps down to 1 or 2 in vanilla flow matching, the accuracy just completely collapses.
I mean, it's like drawing a complex curve by connecting hundreds of tiny dots. If you try to do it in one single step.
Just drawing one straight line?
Yeah, exactly. You completely miss the arc of the curve. And in physics, missing that arc means losing all the high-frequency structural details that make the simulation accurate.
You lose the chaotic vortices in a fluid, or the temperature spikes in a climate model. So the authors asked, how do we fix that curve problem without just adding back hundreds of steps?
And they look to classical physics for inspiration, right? The 1D wall-bouncing pendulum.
Yeah, it's a brilliant structural inspiration. Imagine a pendulum hitting a wall at position x equals 0.
Okay, so it hits the wall and bounces back.
Right, and with each bounce, the velocity reverses, and its magnitude shrinks by a retention coefficient, which they call alpha.
Creating a set of progressively attenuated trajectories.
Exactly. So mathematically, the new velocity is just alpha times the previous velocity. Assuming a constant half-cycle duration, the amplitude shrinks proportionally with velocity.
Wait, let me just clarify for you listening at home. The network isn't actually simulating a physical pendulum, right?
Oh, no, not at all. It is purely a structural parameterization. It's just a mathematical scaffold to create multiple, consistent trajectories for self-supervision.
Okay, got it. So RecFM ports this exact intuition into flow matching. Instead of learning a single trajectory from noise to data,
like vanilla flow matching does.
Right. RecFM introduces additional trajectories at different scales, dictated by alpha.
And the brilliance here is that these scale trajectories all intersect at a shared spatial state, x sub t.
Which lets the model enforce cross-scale trajectory alignment.
Exactly. It forces all those trajectories to be mathematically coherent.
So how is this actually implemented under the hood? Like, how is it coded into the loss function?
Well, looking at algorithm 1 in the paper, the velocity network, v theta, is conditioned on space, time, and that scale, alpha.
So conditioning on alpha means a single model represents the entire family of trajectories.
Precisely. The primary trajectory learns the standard noise-to-data velocity, basically x1 minus x0.
And the secondary trajectories.
They're time rescaled, so time is time divided by alpha. And their target velocities are scaled by alpha too.
So the target is alpha times the quantity x1 minus x0.
Exactly. And the total loss function combines the standard trajectory loss with the consistency loss, LCONS.
And that consistency loss mathematically enforces that the predicted velocity of the ith trajectory equals alpha times the primary trajectory's velocity.
You got it.
It's kind of like having multiple GPS systems calibrated to different zoom levels.
Yeah.
You have a city view, a street view, a building view.
That's a great analogy.
Yeah, the consistency loss forces all of them to agree that you're standing at the exact same spatial coordinate at that exact moment. They can't drift from each other.
Right. And they control this with a consistency weight, lambda. The authors found the optimal consistency weight is exactly 1.0.
Wait, really? I would thought you'd want to crank that way up to force them to match.
You'd think so, but if lambda is too small, performance drops, and if it's massive, like 10 to the 6th, it overwhelms the primary flow matching objective.
Oh, so it just forgets how to map noise to data entirely.
Exactly. It ruins the accuracy. They also tested the optimal recursion depth, basically the number of bounces, which they called D.
And what did they find?
D equals 2 is optimal. Pushing it to 3 yielded diminishing returns and required more memory.
So simple pairwise consistency is all you need.
Yeah, it's sufficient.
Okay, so we know what the algorithm is, but from an ML theory perspective, why does this specific formulation actually enable one-step generation?
Two main reasons. First, RecFM acts as massive data augmentation in the conditioning space of the network.
Because every time an alpha pair provides an independent supervisory signal.
Right, for the exact same underlying directional quantity at that spatial point.
Okay, and the second reason?
This is the critical one. Minimizing the consistency loss mathematically constrains the temporal derivative of the velocity.
Meaning the model actively drives the trajectory acceleration to 0.
Exactly. It literally straightens the ODE trajectory.
Oh, wow. And a straight line trajectory means a single-step Euler integration doesn't suffer from truncation errors.
Exactly. You're just taking one straight step, so you don't miss the curve because there is no curve.
That is incredibly elegant. But wait, how does this differ from other one-step methods like shortcut models?
So shortcut models regularize via spatial composition. They basically force one spatial step of size t to equal 2 steps of size d.
Oh, whereas RecFM regularizes via cross-scale coherence.
Exactly. And in the paper's Helmholtz benchmark, RecFM significantly outperformed the shortcut model.
Probably because shortcut models are designed more for static images, right? Not dynamic spatiotemporal physics.
Right, exactly.
Okay, so that brings us to benchmarks and real-world emulation. ML engineers ultimately care about deployment. How does RecFM actually perform on physical data sets?
They evaluated it across 3 distinct data sets. First, sea surface temperatures, or SST, which is real-world, highly stochastic climate data.
Very noisy.
Very. Second, Navier-Stokes, which is deterministic fluid dynamics with complex turbulence.
And the third?
The Helmholtz staircase. It's a higher-order analytical acoustic scattering data set.
So a pretty rigorous test. How did it do compared to the state-of-the-art?
Operating in just 1 to 2 steps, RecFM matches or beats multi-step solvers across the board. It achieves a 20x speedup over diffusion.
Wow, 20x.
Yeah.
Which is crazy because RecFM doesn't even use explicit physical equations during training like PBFM does.
Exactly. And crucially, RecFM actually preserves physical laws better than iterative solvers.
Wait, really?
Yeah. On the Navier-Stokes dataset, RecFM maintained the average kinetic energy of the system far better than PBFM.
It's completely counterintuitive. We usually assume that taking more steps makes the simulation more physically accurate.
Right, but RecFM proves that if you structure the trajectory correctly during training, taking fewer steps actually prevents error accumulation.
Because iterative solvers accumulate error with every single step they take.
Exactly, and we see the same thing on the Helmholtz dataset. RecFM achieved significantly lower PDE residuals.
I did notice, though, that the advantage of RecFM is most pronounced on deterministic PDE problems compared to the highly stochastic ones, like the sea surface temperatures.
Yeah, that makes sense because few-step flow matching is inherently more deterministic. It doesn't inject as much randomness.
Right. But regardless, RecFM successfully breaks the speed-fidelity trade-off in scientific computing.
It really does. It offers a scalable, real-time emulation solution that doesn't require explicit PDE formulas.
Which leaves us with a final, slightly crazy thought for you to mull over. If RecFM is able to mathematically force complex trajectories to straighten out without explicit physics equations, could this multi-scale trajectory alignment be the missing link for stable, one-step generation in non-physics domains?
Oh, like where?
Imagine applying RecFM to high-resolution long-form video generation. The governing equations of human semantics and motion are entirely unknown there.
That's a fascinating idea.
Right. If we can bounce a theoretical pendulum to solve Navier-Stokes in one step, what else can we bounce?